Hello everyone and welcome back to the Mammoth Interactive YouTube channel. This is Alexandra from Team Mammoth. In this lecture, we are going to talk about gradient descent, a visual approach, as well as stochastic gradient descent. Before we jump into this video, go to the first link in the description because we're running a Kickstarter, Excel, machine learning, and blockchain in 99 days. Don't miss out. Two very popular techniques in machine learning, very important as well for understanding machine learning in general. Stochastic gradient descent is an offshoot of gradient descent. So let's start by talking about gradient descent in general. The goal of gradient descent is to minimize the loss of a model. And the gradient descent process does this by finding the best possible parameters for a model, and it continually goes in the negative direction, as you can see here in this visualization. Gradient descent will continually go in the negative direction on a graph that has loss on the y-axis and that has the parameters on the x-axis, a parameter such as the weight, as well as the bias. So let's talk about an example that uses a linear model, one of the most simple machine learning models. Let's say we have a bunch of data and it has a linear structure, meaning that its features on the x-axis can be plotted linearly with its features on the y-axis, which are its label. So every sample here has been plotted with x being the features of the sample and y being the label of the sample. And you can see the data has taken a linear shape. But how do we train a machine learning model to be able to give us the exact equation that will be the best fit line through these data points? We know from algebra perhaps that the slope of a line is m in an equation y equals m times x plus b, where m is the slope and b is the intercept. And we know the x and y. We wouldn't have been able to plot the data without the x and y. So we know that we have the x and y from our data set. The model's job is to find the best m and b, where m is the weight and b is the bias, if in machine learning terms. So the model will actually start with a random weight and bias. So it will give you a somewhat random line. The equation is still linear. It's still y equals m times x plus b. Y equals weight times x plus bias. So the equation is still linear, but the weight and bias initially are random because the model doesn't know where to start. So it starts with a random weight and bias. So the equation is random. That's why you get a line initially that doesn't fit well through your data, so your loss is very high. But the model uses gradient descent to slowly get better. So gradient descent means we are going to be using that technique to reduce the loss of our best fit line, to get it closer to actually fitting through the data points perfectly. And gradient descent does this by always going in the negative direction of your loss to parameter graph, as we saw previously here. Gradient descent is going to continually go in the negative direction, reducing loss where you have the parameters on the x-axis. The goal is to find the parameters that give you the smallest possible loss in the model, because those are the parameters that are the optimal parameters for your model. And there you have your model. For example, let's take a simple equation like y equals weight times x plus b, bias. Let's say bias is 0 in this case. The intercept is 0. That means our equation is just y equals weight times x. We know the x and y. Those come from our data set, so the model just has to find the weight, just one value. The model will start off with a random weight, and it's going to get the loss for that weight equation. Then it's going to try a different weight that is close by, and it's going to see if the loss improves or decreases, which is the same thing. If the loss decreases, it means the model improves. If the loss increases, it means your model has performed worse. So gradient descent will check, did the model perform better or worse? And we use a loss function such as mean squared error to do that. We calculate the difference between the model's prediction and the actual label. For example, a sample might have a label 2, but the model may have given the label 4, so you're 2 units off, which means you have a lot of error. So the model has error initially because it has a random function initially. But then the model is going to adjust its weight and it's going to check, did the model improve or get worse? If the model improved, gradient descent knows that we are going in the correct direction, and it will again adjust the weight, and it will see, does the model improve or does the model get worse? And then it will do it again and again and again. It will continuously adjust that weight, that parameter, and in this example we just have the one parameter, the weight, but you can have a lot of parameters in your model depending on how complex the model is. So gradient descent will keep adjusting that weight, that parameter, until it finds the best possible parameter, because it has found the best possible loss, the smallest possible loss, meaning the highest possible accuracy. Once the model has definitively found that smallest possible loss with gradient descent, that's when we know we have found the optimal possible model for our data set. All right, so here we have a graph of loss versus weights, which gradient descent will have created, because gradient descent will try out different weights or parameters, and it's going to plot the loss for each of the weights. And you can see there will be this curve. Typically, there could be many curves in the gradient descent, because if your weight is too small, your loss will be high. If your weight is too big, your loss will be high. You have to find the best possible weight, and it's always different depending on the data set, depending on the model type. The parameters will always be different each time you build out a model. So gradient descent finds the best possible parameters because it has been able to find where the loss was smallest. And therefore, it gets a little bit closer to the best fit line until eventually it has the best fit line. It has that line that goes through the data points as perfectly as possible. And that is how gradient descent works in machine learning. You can see it's actually fundamental to machine learning. Without a technique like gradient descent, being able to find where the smallest possible loss is, we wouldn't actually be able to find the weight and the bias unless we used a different technique. But gradient descent is extremely fundamental. It's what actually finds the machine learning model, because the machine learning model itself is just a mathematical algorithm. It's just an equation. In this case, it's something as simple as y equals m times x plus b. So it's just an equation, and without gradient descent, we wouldn't be able to find that perfect equation, and we wouldn't be able to perform machine learning. Stochastic gradient descent is just a slight variation on gradient descent. There are many variations. So with gradient descent, we're using all of our samples each time we do that little tweak of the weight and the bias or any parameter. This can be very consuming of power, computational power, time, if we're using all the samples every single iteration that we are adjusting that weight and that bias. So if you have a massive data set, if you're some huge company, some huge data collector, you have a lot of data, gradient descent may be extremely slow. So use stochastic gradient descent, which just means you use only one or a subset of your samples. And you might be thinking, how can I only use a subset of my samples or one sample when I have this huge data set? Well, the answer is that you're going to be using that one sample or that subset for each iteration. And stochastic gradient descent, it will have a worse performance, but it will eventually get to the same result because it'll oscillate around the same result as gradient descent. There's a lot more that you could learn behind the math behind stochastic gradient descent, the math behind gradient descent, but for the purpose of machine learning, you just have to know at least the basics to be able to start building models. As you want to build more advanced models, you can learn more about the math behind stochastic gradient descent and gradient descent, but it's not required to get started. That is gradient descent in machine learning explained visually. Don't forget to check out our Kickstarter first line in the description where you can learn a lot more about